Welcome to an introduction to the CANopen interface, as well as the J1939 interface. We'll be covering the basics of the CANopen interface in terms of commands, as well as the command style for the J1939 interface. A few products that we have to offer that actually utilize the CANopen and J1939 interface. And then at the very end, we'll be doing a live demo with a CANopen encoder just to show you some commands that you can send and how to negotiate the device into the various modes. The contents of this presentation include the beginnings of when CANopen was developed, like the topology of your CANopen network, operating needs plus network management commands, the command structure for the parameters, reading and writing parameters with the SDO, as well as looking at mapping your TPDO, your process data output. We'll also discuss heartbeat and guarding for the CANopen devices on the network, and also an overview of the available devices that we have to offer for CANopen and J1939. The first iteration of CANopen was developed in 1994. It was CANopen specification CIA 301. CANopen is a two-wire differential bus system. You have a two-wire circuit for communication and a two-wire circuit for power. It utilizes a 5-conductor cable overall. Every node on a CANopen network is considered a consumer and producer. So nodes can talk to all the other nodes on the network, but then a master can also talk to all the nodes on the network as well. Baud rate for CANopen is variable between 10 kilobits and 1 megabit. So very fast speeds are capable for this interface. And then CANopen lets you address up to 127 nodes per network. The topology of a CANopen network is demonstrated on the screen. You basically have each of your individual nodes attached to the line. You have a two-wire circuit for the communication, like I stated earlier, and then a two-wire power circuit. A common pinout on a cable for a CANopen network is also shown on the screen. You typically use shielded twisted pair wire to try and dissipate any noise that may happen on the line. Termination is required on both ends of the network for a CANopen style network. You can see that I have 120 ohms on both sides of the network. And then lower node addresses do have a higher priority on the CANopen network. So if you have a device that requires a higher priority than other devices, you want to make sure that it has a lower address, preferably set closer to 1 for all the addresses on your CANopen line. So we already looked at the baud rates that you can have on the CANopen network between 10 kilobits per second and 1 megabits per second. While the baud rate can be very high at that 1 megabit per second, it does limit your max bus length. So the screen shows a recommendation of the max length of cabling for your system in comparison to the baud rates. You don't want to really exceed these lengths if you have higher baud rates than typical. Typically, in most applications, the 250 and 500 kilobits per second would be the default. If you do go to the 1 megabits per second, that is a very fast speed, and your line definitely needs to be limited, and the cable needs to steer clear of any high voltage lines, essentially. CANopen network management has 4 categories for the device states that each node can be in. So we have boot up, pre-op, operational, and stopped mode for the devices. Now, in a pre-op mode, the device is in a boot up state. No PDO, no process data is actually being exchanged between the master and the node, but parameters can be read and written to via commands. Operational mode is the same as pre-op, except now we actually have process data being exchanged between the device and the master. And then in a stopped mode, no process data is going to be exchanged between the node and the master. And also, you can't read or write any parameters for these devices. So now we're getting into the actual command structure for CANopen. So this is a very vague breakdown of the command structure for CANopen command. You have your CAN ID, you have the length of the designated command that you're sending, whether you're reading or writing a parameter. and then you have your data filling the next 8 bytes of information in the command. So these are basic commands, just like the NMT commands, the network commands that we were talking about earlier. You can see I've outlined the major ones, which would be a stop state command, a pre-op, and an operational state command. Notice that my CAN ID is all zeros. So what that does whenever you have devices on the line and your CAN ID is all zeros and you're sending out these commands to either switch the device into an operational, pre-operational state or a stop state, that's going to change every device's state along the line. The lower command that is stating it's an operational state for address 2 specifically, you see how that's a 0-1 for a command, but the 0-2 is designated that it's only targeting address 2 in this case. With CANopen, we have 2 main categories. They are service data object and process data outputs. So for a service data object, that's where you're actually reading and writing the parameters of the device. The parameters can be exchanged from the device to the master or the master to the device. Either way, again, everything's a consumer and a producer on a CANopen circuit. Your process data output is offered when the device is in an operational mode. You see we have TPDO, which is data from the device to the master, and RPDO, which is data from the master to the device. The example shown up on the screen is an example of reading parameters out of the SDO. In this case, it's a simple position value request for the device. So this would be like an acyclic position value request from the device. You can see the command I outline above and below, whether it's the command up in the top right-hand corner or the response down below. I outline that I'm using the 600, index 600, plus my CAN ID, which is 20, hex 20, which would be decimal 32, which is the default node ID for this particular device. You can see my command string with 40 hex, and then I'm pulling from index 2000, subindex 0, and then I get a response back down below with my actual position value for the device. Now, this is an example using the SDO to write a parameter. In this case, I'm changing the resolution per revolution on this encoder. So if we focus on the command down below in the response, you can see that my command is 23. I'm pulling from 2101, index 2101, subindex 0, and I'm writing a total resolution per revolution for it. The response I get back is a happy response from the encoder, and if I were to read back the parameter, I should get the same value that I entered for writing to the device. So now we have a slide discussing the TPDO of the CANopen device. There are 2 different types of TPDOs. You have your transmission type and you have your mapping. Transmission type is going to deal with setting certain parameters for that process data output, and then your TPDO mapping, the process data mapping, is going to be the output data of the device. So covering more into the individual parameters you can actually set for TPDO, this is an example using one of the encoders that I have, one of the CANopen encoders. So you can see you have 5 subindexes for this particular device. You can set your COB ID. You can set your transmission type, which is that chart on the lower right-hand corner of the screen. That's basically going to allow you to either have the device produce process data back to you automatically, or it can be like a software trigger where the device will only produce it whenever requested. You also have an inhibit time for these devices where you can tailor how much time is before process data output will actually become available from the device. And then you can also have an event timer on here, which is something we would have to refer to the manual for the device. Heartbeat and guarding are very useful features to alert the user of the CANopen network to whether or not a node might have fallen off, might have gotten damaged, something along those lines. With a heartbeat on a particular device, a device is constantly sending out a message at an interval, and the master is monitoring that message. If no heartbeat is detected, no message is detected, then the master can alert the user of the network. Guarding is the opposite. A master is requesting updates from the nodes, and if no response is gathered back from the nodes, then it alerts the user of the CANopen network. So the same concept, and they're both very helpful in determining the health of your network. So now we're going to cover some of the CANopen devices that we have to offer as part of our portfolio. The ENA42 HD series is one of our most durable encoder styles. It was developed for mobile equipment applications. It uses a magnetic style technology versus an optical style technology, which is a lot more durable in terms of shock and vibration. It also has a really good IP rating. It's wash down and waterproof, along with a stainless steel housing. We offer LiDAR scanners with the CANopen network. This is the R2100. It gives you 11 individual fields, 88 degrees of total area of total coverage, along with an 8-meter range. It's used quite often on AGVs, scanning a large area in front of the AGV, and it's also very friendly on the CANopen network since realistically you're only monitoring 8 individual beams. PGVs for CANopen again on AGVs. The CANopen interface is very popular. With the CANopen PGV, it offers you absolute positioning and angular positioning on a device that's non-contact with the floor. So it is quite a durable piece of equipment since there are no mechanical parts that can produce wear. So getting into more narrow variations of the CANopen network, we move on to J1939. So J1939 cannot exist without CANopen. It's kind of like having a car, and CANopen is the car, and J1939 is like the tires of the car. J1939 is just another level of the CANopen interface. So with J1939 and CANopen, they both use the same ISO standard, but J1939 adopted a 29-bit frame format, which we'll cover. CANopen also only allows up to 127 nodes. J1939, with the extended format, allows 254 nodes. J1939 also has some other more specific versions of itself, where you can see I listed two there, -11 and -14, and they specify very specific baud rates be used in the application. The 29-bit extended frame format is demonstrated on the screen. Your priority in your extended data page bit and the data page bit are specific to the device, so you have to refer to the manual for the command. The PDU format, that's specific to the destination address, and you should also refer to the manual of that particular J1939 device to make sure you have the command correct. And then you finally just have the destination and the source address of the command that you're using. And this is a more detailed breakdown exactly of how that's going to happen. And I believe that this was taken out of a manual for a ENA 42, but the J1939 version. The product I'd like to highlight at the end of this presentation is the new IMU inclination sensor. The IMU is a much more advanced inclination sensor than previous inclination sensors we've offered. It uses the same technology as previous inclination sensors, where it uses accelerometers to determine angle as well as acceleration of the device. However, when the older models were moved, during that movement to the new angle that it was being transferred to, you would get large spikes in the output of the movement. It couldn't really maintain a smooth, gradual monitor of the device while it was in motion. That all changed with the new IMU series with the addition of a microscope. So lots of mobile equipment applications where vehicles are braking, accelerating, or running over things on the road, or going over uneven ground, monitoring the movement of large arms on vehicles like backhoes and front end loaders are all possible now with this technology in real time, as well as even monitoring like steering angle of a vehicle's steering column. Since this is a mobile equipment sensor, it does have very good outdoor and offshore ratings. So it's washed down and waterproof. It has an extended temperature range down to -40°C, which is very nice. And then it also has an extended voltage operating range down to 5 volts, which you need for mobile equipment applications. This is a demonstration of the process data output you would end up seeing on this device. You can see you have quite a few process data outputs that are going to sort of flood the network very, very quickly. It's a lot of information, but since it's a lot of information, it's also extremely helpful in a lot of applications. This is definitely a very high-end technology and is already proving very useful in the field in terms of mobile equipment. Let's begin with the software demo of the CANopen software. And the device I'm working with today is an ENA42 CANopen. It's a very, very easy device to work with. All of the commands I'm going over today are going to be entered manually. The software I'm going to be using is CANopen Device Explorer, which is very helpful demo software that you can actually load in an EDS file for the CANopen device. CANopen devices do use EDS files, electronic data sheet files, just like Ethernet IP devices would end up using. So the first thing I want to do is I want to get the device connected, which I already have connected, and then I want to see what type of state the device is in and whether or not it's recognized on my line. So I can currently see that the LED indication on my device is flashing green. That's a good sign. That means that I'm currently in pre-operational mode with the device on my line. And that means that the line is healthy. There's no like bus heavy scenario where maybe my termination on the network is incorrect or anything like that. So what I want to do first is I want to actually go ahead and I want to put the device into an operational state. You can see here I have all of my commands already outlined in the software, and negotiating between a 0, 1, 80 and 0, 2, like I mentioned earlier with those networking commands, that'll move me between operational state, pre-op, and stop mode. The 0x20, that's hex 20, which is decimal 32. And that is going to be my node ID for this particular device, which is the default is decimal 32. You can see here on this particular command, the CAN ID is 0. That is because I'm sending this command to everything on my network. Now, I just have one device on my network, so I can do this pretty easily without too much of a headache. When using these commands on your line, if you have multiple devices, you might want to actually target the device on the line for the specific node ID. So I'm going to go ahead and I'm going to transmit that. You can see the encoder is actually instantly producing position data. I'm turning the shaft and you can see it changing on my count. So I'm going to go ahead and put it back into a pre-operational state so I can mitigate all of this mess of the process data coming back. Transmit that. I'm going to go ahead and clear, and you can see it's no longer transmitting any positional data for the encoder. Now, the first command I want to go over is a simple read position command, acyclic read position command from the device. You can see I'm using command 30 and I'm pulling on index 2000 right here, subindex 0. And what this command is going to do is it's going to actually read the position of the encoder. So you can see right here on my CAN trace, it did produce the position of the encoder back. So that's good. But now what I want to do is I want to get into more of the bigger parameters set for these devices, the ones where you can actually write to them and then read back. So what I want to do here, I want to read the preset parameter that's currently on this ENA42. So I'm going to go ahead and I'm going to do that. So you can see here, my current preset is actually set to 61A8. Now, translated from hex and the decimal, that's 25,000. And you can also see it's index 2103, subindex 0, and then it was a command 40 for reading. So I want to change that though. That 25,000 isn't really a good preset. I want to change that to 100. So I'm going to go ahead and clear that, and I'm going to go ahead and use this command down here, which again, 2103 is what I'm writing to. Subindex 0, and then 64, which is decimal 100, is part of the command. And I'm using command 23. So I'm going to go ahead and I'm going to transmit that. So you can see I got a response back from the encoder. Everything looks good in terms of the response. But just to make sure, I want to go ahead and I want to do a read back. And you can see I did a read back to that same index, subindex, and I got back a 64, which is perfect. That means that it actually accepted my preset of 100. For this device in particular, though, I will have to do a save that I don't have on here because it's just not necessary as part of this demo. Let's go ahead and do a retransmission type command next. Remember when I stated earlier, the transmission type sort of gives you the ability to either get that process data back from the device automatically, or it would be like a software trigger, like a request from the master. So let's just go ahead and read that. So currently I am in a state of FE, which is the default. It's 254. So what that means is that you saw earlier the process data is going to automatically be produced back from the device. But what I want to do is I want to kind of change that to a 252, which is FC. So I'm going to go ahead and I'm going to write that to the device. So let's do that. Okay, everything looks good. Let's go ahead and read back my transmission type just to make sure. Yep, you see that right there. FC came back. That's good. Now what I'm going to go ahead and do is I'm going to go ahead and I'm going to put the device into an operational state. So if you remember earlier when we put it into an operational state, it instantly produced a bunch of PDO data. Now whenever I submit the command to put the device into an operational state, it's not actually producing any data because it's waiting for the master to request that data back, which is a separate command. So what I'm going to go ahead and do is just change this back to a pre-op state. So 80, perfect. And I can even tell based on the LED indication of the device that it's back into a pre-op state. I am going to go ahead and change this back to an FE, which is my 254. I'm going to transmit that. Everything looks good. I am going to then read it back to make sure that it is set correctly. Whoops. There we go. FE, that's perfect. And now I'm going to go ahead and I'm going to put the device back into an operational state using a 01, transmit, and now all of my data comes flowing back. Notice also that the device now shows a 64 hex only for position. That's because we just preset it to that 100. But again, you will have to do a save parameter to make that stick. So let's go ahead and put the device back into an 80 for pre-op. I'm going to go ahead and transmit that. I'm going to clear it. Everything looks good. The encoder's happy, healthy, and the LED is flashing correctly. And that is the basic overview of how to use sort of like the really simple commands for these CANopen devices to get them to change parameters and or get them in and out of the various stages that you can. If you have any questions, feel free to contact me about your CANopen network or the CANopen device you have from us. I'll be happy to answer them.